Imagine a land almost entirely swallowed by sand. A nation where over 95% of its territory is desert, and rainfall is so infrequent it's practically non-existent. It is within these formidable conditions that Saudi Arabia has accomplished something bordering on the miraculous. They've constructed a colossal steel artery, a system designed to transport water from the shores of the Red Sea to quench the thirst of the entire country. Every single day, billions of liters of seawater are drawn into vast desalination complexes, then pumped across the desert through a network of pipelines stretching for 1,000 kilometers, carrying life-giving water from the sea deep into the heart of the mainland. The sheer feat of delivering water so far from the coast is an extraordinary engineering triumph. However, it is Saudi Arabia's mastery of transforming salty seawater into fresh, potable water suitable for drinking, agriculture, and industry that has truly earned them the world's admiration. So, how is this invisible river of steel built, and how does it function? Today, we will unravel the secrets of its success together. Over 37 million people call Saudi Arabia home, and the vast majority adhere to Islam. What's particularly striking is that nearly all of the population is concentrated along the coastlines of the Red Sea and the Persian Gulf, while the interior remains a sparsely populated desert. This nation possesses something the entire world craves: oil. Yet, nature rarely grants everything at once. Despite possessing immense subterranean oil reserves, the country is compelled to expend billions of dollars to procure every drop of fresh water. The average annual precipitation here is less than 100 millimeters, and during the summer months, temperatures regularly soar above 45 degrees Celsius. To survive in such an arid environment, Saudi Arabia embarked on building a nationwide water supply system. To truly grasp the magnitude of this undertaking, consider for a moment what it means to live in such a nation. There are no mighty rivers, no large lakes, and no abundant underground springs to rely upon. The sky remains clear for months on end, and the scorching sand stretches to the horizon. Despite this, tens of millions of people require water daily for drinking, cooking, hygiene, irrigating fields, and fueling industrial operations. Ordinary nations receive these necessities from nature itself: rain, rivers, and springs. Saudi Arabia, however, must create everything from scratch, extracting water directly from the sea and forcing it to flow across the desert to where its people reside. In essence, an entire civilization thrives thanks to a man-made system. Without it, life here would simply cease to exist. This network is assembled from high-strength carbon steel pipes, akin to those used in the oil and gas industries. The construction costs an average of approximately $3 million per kilometer of pipeline, and this figure excludes the cost of the pumping stations that propel the water onward, as well as the desalination plants themselves, each of which can cost tens of millions. But where does this pipeline draw its water from? The answer? An almost inexhaustible source: the sea. The challenge, however, is that seawater contains around 3.5% salt, making it far too saline for consumption or agricultural use. This is precisely why desalination technology has been developed, providing Saudi Arabia with a virtually limitless supply of usable water. The pipeline carries water from enormous desalination plants situated directly on the Red Sea coast. A single plant can transform millions of liters of seawater into potable water daily, consuming an immense amount of energy in the process. Energy is the critical and most expensive resource here. To force seawater through membranes and extract the salt requires pumps of immense power, operating continuously day and night. This is why desalination is considered one of the most energy-intensive methods of water procurement globally. Saudi Arabia, in this regard, is fortunate. It has access to inexpensive fuel, and it dedicates a portion of its vast oil and gas reserves to the very purpose of converting saline seawater into drinkable water. It's a form of exchange. The nation generously expends one of its abundant resources to acquire another that it desperately lacks. But let us proceed step by step. The initial phase in constructing this transcontinental aqueduct involves the fabrication of the pipes themselves. They are typically manufactured from high-strength carbon steel, similar to that used for oil and gas pipelines, ensuring they can withstand the constant pressure of pumping, mechanical impacts during underground installation, and the harsh temperature fluctuations of the desert. Rectangular steel sheets are cut to precisely calculated dimensions, enabling them to be rolled into cylindrical pipes approximately 1.8 meters in diameter with a wall thickness of nearly 25 millimeters. These sheets are then fed through a multi-axis rolling mill, where rollers gradually bend the steel until the two edges meet, forming a pipe blank ready for the next stage, longitudinal welding. Following welding, the pipes undergo a direct water cooling process to reduce the temperature of the weld seam. Subsequently, the steel pipes are meticulously machined along all edges and corners, removing any burrs and achieving precise geometry. Both ends of each pipe are beveled to create an ideal surface for future joints. Each pipe section typically measures around 12 meters in length, a dimension sufficient to minimize the overall number of welds while remaining manageable for transportation. This length facilitates rapid connection of pipes, ensures leak-proof performance under pressure, and guarantees long-term durability. It is important to understand why such stringent requirements are imposed on these pipes. Beneath the desert sands, several adversaries lie in wait. During the day, the sand heats up intensely, only to cool sharply at night, causing the metal to expand and contract. This cycle repeats year after year, with the pumped water exerting constant pressure from within and the weight of the soil pressing down from the outside. Furthermore, if left unchecked, the water itself can corrode the steel over time. This is why the pipes are made from exceptionally strong steel and are coated with protective layers to ensure this underground conduit serves reliably for many decades, remaining unseen and unnoticed by those who benefit from its water. The finished steel pipes are transported to an open-air storage yard where they are stacked in batches and clearly marked for inventory and tracking. From there, forklifts or cranes lift them onto specialized transport vehicles and secure them firmly to prevent deformation during transit. Finally, the pipe sections are hauled hundreds of kilometers to the construction site, where they are welded together along the planned route of the future pipeline. The actual laying process begins at large staging areas established along the route. Here, the completed pipe sections are sorted by diameter, length, and installation sequence. Engineering crews then conduct a final inspection, verifying the alignment of the pipes, the condition of the coating, and the identification markings. Strict order at such a site is paramount. It allows for uninterrupted work, minimizing delays and errors in the harsh desert environment. Meanwhile, surveying teams precisely mark the pipeline's route across the desert, utilizing satellite navigation, total stations, and topographic data. The line of the route is marked directly on the ground with stakes and bright paint. This stage ensures the pipeline follows the most stable and advantageous path, avoiding unstable soils, areas of shifting sands, and regions prone to erosion. For a pipeline spanning hundreds of kilometers, selecting the correct route is everything, as the longevity of the entire structure depends on it. Before trenching begins, the site must be cleared and leveled to allow heavy machinery to operate unimpeded. Temporary access roads are constructed parallel to the pipeline for trucks, excavators, welding machines, and material transport. Preparations also include measures to combat dust and quicksand, ensuring good visibility and worker safety. This forms the foundation for all subsequent construction. Once the route is definitively established, large tracked excavators commence digging trenches along the marked line. These trenches are excavated to a precisely defined width and depth, providing ample space for pipe installation and subsequent backfilling. The excavated soil is immediately sorted. Usable material is set aside for backfilling, while unsuitable material is removed. Maintaining a uniform depth and a straight trench line is crucial, as any deviation could lead to pipe deformation or displacement after installation. In some areas where the route crosses steep, precipitous mountain slopes, the trench is carved directly into solid rock using explosives. Charges are placed in precisely calculated locations and detonated sequentially to fracture the rock along the intended line. The resulting explosion creates a trench deep and wide enough to securely lay the pipe, even in places where conventional machinery would be ineffective. This allows construction to proceed through the most challenging landscapes, securely burying the pipe underground. After trenching, the pipe is not laid directly on the trench floor. Instead, a layer of selected material, typically fine sand or screened soil, is spread evenly across the entire bottom, creating what is known as a bedding. This layer evenly distributes the load and reduces stress on the pipe. The bedding is leveled and lightly compacted to achieve the desired height. In desert environments, with their loose and dry soils, this step is particularly vital for the long-term durability of the entire line. For laying large diameter pipelines, a construction corridor approximately 40 meters wide is prepared in advance. This allows for continuous laying with an average speed of about 1.5 kilometers per day. The pipe sections are approximately 18 meters long, minimizing the number of field welds. While this imposes extremely high demands on lifting, transportation, and precise fitting at all stages, at the welding site, a hydraulic centralizer is inserted into the pipe joint, and its clamps are expanded to 36 degrees around the entire circumference, holding the two sections perfectly coaxial, both before and during the initial root pass weld. Automatic welding is then employed, operated by approximately 80 individuals and dozens of specialized machines. Such a crew is capable of completing up to 150 joints per day on pipes with a diameter of about 1 meter. Once welding is complete, each joint undergoes automatic ultrasonic testing to ensure there are no internal defects. Subsequently, the joint coating crew cleans the surface with abrasive blasting and applies a multi-layer liquid epoxy coating, forming a robust and completely watertight protective layer. Only then are the pipes lowered into the trench and backfilled. The assembled pipes are lowered into the trench using pipe layers, specialized tracked machines designed precisely for laying large diameter pipelines. Several such machines, equipped with side booms, work sequentially along the line, each lifting its section of the pipe string using soft slings and steel cables to avoid damaging the coating. The string is lifted evenly and held suspended above the ground as the machines slowly move along the trench. The coordination of the operators is critical here, as even the slightest error could lead to twisting, bending, or contact with the trench walls. Once the pipe is precisely positioned, it is lowered gradually, centimeter by centimeter, until it rests in the center of the trench on the prepared bedding. Throughout this process, surveyors meticulously monitor the elevation, alignment, and natural sag of the pipe to prevent residual stresses from developing. This method allows for rapid, steady, and highly accurate pipe laying, ideal for long, straight stretches across the flat desert. After the pipe is laid, the trench is backfilled in several layers. The first layer consists of fine material to protect the pipe coating, followed by the previously excavated soil. Each layer is mechanically compacted to achieve the desired density, preventing future ground settlement. In desert conditions, where wind and extreme temperatures affect soil structure, proper compaction plays a crucial role in the pipeline's longevity. Thus, gradually, section by section, through sand and rock, this steel artery is laid, destined to carry water across the entire country. But laying the pipe is only half the battle. The water must be propelled for thousands of kilometers, and in some places, it must be lifted over elevations far from the coast. It will not flow that far on its own. Therefore, at regular intervals along the entire route, pumping stations are installed, acting as powerful hearts for this system, repeatedly picking up the flow and pushing it onward, maintaining the necessary pressure. Without them, the water would run out after just a few tens of kilometers. It is these stations that transform the static steel pipe into a living, flowing artery, reaching the most remote corners of the nation. However, all of this would be of little consequence without the other end of the system, the part that draws water from the sea itself. It all begins with seawater being taken directly from the open ocean and directed inland, establishing a steady and uninterrupted flow of raw water to the desalination plant. Initially, large intake pipes are positioned offshore, where assembly crews carefully place each section before lowering it into position using powerful cranes operating from barges or coastal platforms. As the pipeline extends towards the shore, individual sections are sequentially joined into a single continuous channel designed to withstand constant hydraulic stress. At this stage, precision joining is paramount, as even the slightest deviations can impact the line's performance and capacity over time. Once assembly is complete, the water intake is reinforced with support frames and securely anchored to the seabed. The desalination process itself begins when seawater is drawn through pipes leading to open intake screens. Water is drawn hundreds of meters from the shore, where screens and filters at the entrance trap large floating debris and prevent marine life from entering. A 63-centimeter diameter pipe can draw up to 15 million liters per day, which is over 10,000 liters per minute at the point of intake. Powerful pumps drive the seawater towards the plant. However, along with the water, unwanted guests sometimes appear: jellyfish, crabs, and occasionally small fish. To prevent these creatures from entering the system, a large screen is installed in their path, blocking anything larger than 4.5 millimeters. After this, the water passes through finer screens that filter out other large particles. The water intake is also designed to minimize harm to marine life. The suction speed at the intake is intentionally kept low, so fish and other inhabitants are not drawn into the pipes along with the flow, and the screens capture anything reasonably large even before it reaches them. After all, the plant draws truly enormous volumes of water from the sea, and without these measures, all coastal life would suffer. So, at this very first step, even before any purification, engineers must consider not only the purity of the future water, but also how to avoid harming the sea itself. Even after large organisms are screened out, the water is still full of suspended turbidity. The solution is a filtration process that takes place in special tanks. Here, the water flows downward through layers of sand by gravity. The gaps between the sand grains are so small that only water can pass through, while suspended particles get trapped. Simultaneously, the sand continuously moves downward against the water flow, and the dirt settles on its surface. After this stage, the water appears clearer, but it still contains countless microscopic particles. Everything larger than approximately 1/10 the thickness of a human hair is removed. Then, large paddles mix the water and two substances are added: sodium hypochlorite as a disinfectant and ferric chloride as a coagulant. The coagulant causes the microscopic sand grains and dirt particles to clump together into larger flocks, which then settle to the bottom of the tank. Most of the dirt has been removed by this point, but the water is still far from the purity required for the next step: desalination. After passing through fine filtration, the water enters a cartridge filtration system. This is the last line of defense before reverse osmosis. Inside each housing are several cartridges made of densely compressed fiber layers with pores as small as 1 to 5 microns. Water flows from the outside to the inside of the cartridge, and microscopic particles get trapped between the fibers, while purified water passes through the wall and flows onward. As soon as a cartridge becomes clogged, engineers remove and replace it to ensure the system always operates at full capacity. Next, the seawater proceeds to the most critical stage, separating salt from water. Removing salt is extremely difficult because its ions are tightly bound to water molecules by electrostatic attraction. To break this bond, the system must create immense pressure. If you were inside such a desalination plant, you would undoubtedly be impressed by its scale. It is not a single installation, but entire rows of identical blocks stretching into the distance. Hundreds and thousands of membrane modules working in unison. Pumps hum. Water rushes through pipes under enormous pressure, and countless sensor readings flicker on control panels. All of this machinery operates around the clock, 7 days a week, without holidays. After all, if it stops, entire cities risk being left without water. In essence, we are looking at a true water factory that tirelessly transforms the salty sea into something that no human can live without. This is where the real magic begins, a process known as reverse osmosis. Its principle is simple: apply pressure greater than natural osmotic pressure and force water through an ultra-thin membrane, leaving salt and other impurities behind. To generate this pressure, the plant uses powerful centrifugal pumps. Each unit of the pumping system is responsible for a specific pressure stage, and the pressure gradually increases as the water passes through one compression stage after another. By the time the water exits the final stage of the pumping unit, the pressure reaches approximately 60 bar, which is about 60 times higher than atmospheric pressure. This is sufficient to separate water from salt at a molecular level. After the initial pass through reverse osmosis, the water is almost salt-free. but it still contains traces of ions and microscopic impurities that must be completely removed to meet drinking water standards. Therefore, the water is passed through a second stage of reverse osmosis, where even finer membranes operate under lower pressure but separate salt even more effectively. This stage reduces the water's electrical conductivity to extremely low values, extracting the last remaining ions and bringing the water to a state of true purity. The result is a flow of ultra-pure water of almost impeccable quality, ready for mineral enrichment and distribution. But desalination also has its downside, which should be honestly addressed. After all, if fresh water is extracted from seawater, all the salt that was in it does not disappear. It remains in a thick, heavy brine that must be returned to the sea. This brine is far saltier than ordinary seawater. If discharged carelessly, it can harm all living organisms along the coast. Therefore, efforts are made to dilute it thoroughly and disperse it to prevent it from accumulating in one place. So, transforming the sea into drinking water is not only a triumph of engineering, but also a constant search for balance with nature. It is true that after passing through reverse osmosis membranes, the water becomes sufficiently pure for irrigation. However, before humans can safely drink it, its acidity must be adjusted. To achieve this, the plant adjusts the pH level, typically by adding a small amount of acid or a balancing solution, to bring the water within safe limits. Furthermore, desalinated water contains far fewer beneficial minerals than ordinary drinking water. Therefore, to improve both taste and overall quality, minerals such as calcium and magnesium are added during remineralization. This step restores the water's mineral content, corrects acidity, increases alkalinity, and returns the water to its natural taste, making it not only safe but also more beneficial and pleasant for people. It is worth taking a moment to survey this entire system as a whole, from the distant marine intake, traversing tiers of screens, tanks, sand filters, and membranes, propelled by robust pumps through numerous purification stages, and continuing through steel conduits stretching beyond the horizon, cutting through sands and rock to reach cities nestled in the desert's core. This is a single, seamlessly functioning apparatus, stretching for 1,000 kilometers under 24-hour surveillance by engineers, sensors, and control systems. Should pressure falter anywhere or a filter become clogged, notification is instantaneous. This colossal undertaking operates ceaselessly, all for the sake of ensuring that a common resident, hundreds of kilometers from the sea, has pure water flowing from their tap. And so, after its arduous journey, desalinated water finally enters residential areas via a modern pipeline network to serve the people of Saudi Arabia. However, the cost of this water is exceptionally steep, approximately $5 per cubic meter. In contrast, in, for instance, the United States, the same volume might cost merely a few dozen cents. Behind every sip of fresh water here lie colossal plants, 1,000 kilometers of steel piping, immensely powerful pumps, and astronomical energy expenditures. It is at this price, in the heart of a scorching desert with scarce rainfall, that life-giving moisture is born. Yet, for a nation largely consumed by sand, this expense is not extravagance, but a matter of sheer survival. There is simply no other method to quench the thirst of an entire populace. This is that very unseen river of steel, one of the most remarkable engineering feats of our era, transforming the saline ocean into a font of life for a nation. If you found this glimpse into this astonishing process intriguing, please stay with us.